From the Library of Congress in Washington, D.C.
Good morning. I'm Jennifer Harpster. I'm a reference and research specialist here at the Library of Congress with the Science, Technology, and Business Division. I'd like to welcome you to today's program, Magnifying the Universe. This program is the opening lecture for the 2014 Spring-Summer Science Lecture Series. It's also the first program for a series of lectures that are presented through a partnership with NASA's Goddard Space Flight Center. And I am super happy to report that this is our 8th year partnering with Goddard. It's my pleasure to introduce today's speaker, Dr. Jane Rigby, an astrophysicist at Goddard and a deputy project scientist for operations for the James Webb Space Telescope. Before joining Goddard, Rigby was a Spitzer Fellow and a Carnegie Fellow in Pasadena at the Carnegie Observatories. Dr. Rigby received her bachelor's degree in physics and astronomy/astrophysics with the most highest distinctions at Penn State. Her master's and doctorate work in astronomy was completed at the University of Arizona. She is the author of 70 peer-reviewed papers and recently received the Robert H. Goddard Award for Diversity and Equal Employment Opportunity and the Robert H. Goddard Award for Exceptional Achievement for Science. She has given research talks at universities and institutions from California to Halifax. As an advocate for public outreach, you can find her speaking about astronomy, science, and diversity at TED Talks, public libraries, public schools, and now here at the Library of Congress. Today's lecture will take us on an exciting journey to the stars and galaxies billions, and I said billions of light years away. Not millions, billions of light years away. Dr. Rigby will describe the use of gravitational lensing that allows scientists to study parts of the distant universe that are billions of miles away, and they're otherwise too small or faint to be seen. We'll also get a preview of recent results from Hubble and Spitzer space telescopes. So please join me in welcoming Dr. Jane Rigby to the Library of Congress.
All right. Thank you. It's really great to be here. I've spent a couple days at the Library of Congress in the manuscripts division on NASA business, interestingly enough. That's a different story, but that was a real pleasure to get to do that. I've also spent, I need to, now that my son is a little bit older, I need to restart that practice, but I like to come down here to the reading room about once a month and just bring no digital devices and a hard problem and come and think, because I feel a lot smarter in your reading room. There's all that cogitation going on. You feel really smart. Okay. All right, so I'm going to talk about magnifying the universe, and I'm going to talk about how we do that with telescopes that we build and telescopes that are already out there in the universe and we just need to discover. Astronomy is a weird science in a lot of ways because we are linked. We are very much coupled to technological development. We'd like to think that it's the case that we make progress in science, in astronomy, just by being real smart. But you can map what we've been able to learn about the universe to what technologies we've had in terms of telescopes and cameras to study the universe, right? And really it's about building those new instruments and then seeing what they tell us about the universe. And so in astronomy, and unlike, for example, chemistry, where you have a principal investigator, maybe 10 scientists total. They have a chemistry lab that cost $1 million, and they use that, and it's a small group doing that work. In astronomy, we use these resources that cost tens to hundreds of millions of dollars, and so whether or not we like it or not, we have to share. it forces us toward a much more communal way of doing science because we're utterly dependent on these facilities called telescopes. Now, that wasn't always the case. It used to be that astronomy was done by rich dudes who were interested in science, who would build themselves an observatory. And the drawback here is that there aren't that many people that are rich enough to have no actual work to do, so they're free to do it, who care about science and have the math skills to be able to do science. So it used to be that that's who did astronomy, right? These sort of eccentric dudes who built observatories in their backyard. And, I'm being very serious here. You look at the Tycho Brahe, the Herschels, that's how astronomy used to be done. Galileo changed things by taking a telescope, which wasn't that expensive an invention, although he certainly made a lot of money selling his version. And taking that telescope, Galileo did not invent the telescope, but 405 years ago, he was the first to point it up, to observe the heavens, and to write it down and publish it. Not a very big telescope, magnification factors of 10 or 20. So that was something that you needed to be rich, but not that rich, to be able to afford one of the best telescopes on Earth. And so ever since, astronomy has needed these telescopes. This is one of the first college observatories. So you go from rich dudes in their backyard having a telescope to rich universities or colleges having a telescope. This is the Vassar's telescope. That's Mariah Mitchell down at the left. So this is one of these first college observatories. So Harvard College, Vassar got their own observatories. There were also observatories that once people realized the East Coast is a terrible place to put telescopes because it's cloudy and, so the telescopes moved out west in the United States to California. And so you get the Mount Wilson Observatory in California, which is where Hubble, that's Hubble the guy, not Hubble the telescope, where Hubble discovered that the universe was expanding. And he did that from the dark, beautiful, clear site that is now where all the radio transmitters are above Los Angeles. Okay, Mount Wilson, which was dark as all heck when this photo was taken in the 1930s. And so these observatories were still very much kind of like the rich dude in his backyard. Only a few people could use them. And they were, for here, they called this, the dormitories for the Mount Wilson Observatory, the monastery. Women were banned until the 70s. And it was a monastic tradition, and only a few people were allowed to observe. In fact, one of the famous women who observed at that mountain, she didn't actually observe. Her husband, who was a theorist and didn't know which end of a telescope to look through, he was the observer, and she accompanied him and told him what to do. So that's the Mount Wilson Observatory. And so the last 100 years or so of astronomy has been a revolution of going from Hubble the man, Edwin Hubble the person, to Hubble the telescope. Not just in terms of the facilities we have, but in a way of thinking about how we do science. Hubble was operating at an observatory where he was one of a very few people who was allowed to use it. When he died, he willed his data to his successor, and no one else could touch it. So a very hierarchical way of doing science, to the modern way that we do things with the Hubble Space Telescope, where anyone can use Hubble. I'll talk about that in a minute. It's really true. Anyone can use Hubble, and the data are public. And so it's going from that only a few can do astronomy to anyone who has a really good idea and the training to be able to carry it out can do astronomy. So, when we build telescopes now, they are too expensive to fit in someone's backyard, and they're too expensive to be used by just a few lucky people. And that's actually a good thing, because how likely is it that just those few people who have the access are the ones with the best ideas? This telescope is one of my favorites. This is the Magellan twin telescopes at Las Campanas Observatory in Chile. It's as beautiful as it looks. My friend Eva Momcheva took that photo. That's a telescope that's owned by a private institution, the Carnegie Observatories, and operated with several universities. And so, this is a really great place to visit. I've spent, I don't want to count how many weeks of my life on this mountain. You do go and observe. It's a little bit old school that way. This is what it looks like inside. This is the bank of controls that the operator sees. There's an operator who uses the telescope and so that the astronomer doesn't break it, right? Because this is a $100 million facility, and they don't trust me. And they don't trust any of the astronomers. So the astronomer is there and it says, I want my data at all cost. And the operator is there to say, well, that's fine, but the wind's blowing too hard. I got to close to protect the telescope. So the operator sits at this console and is monitoring the status of all the subsystems that run the telescope. The telescope gets refocused every 30 seconds to keep the image as crisp as possible. So it's a really beautiful place to observe, and we have a variety of cameras and spectrographs that are attached to the telescope that we use to get our data. But we really do stay up all night. It's a little romantic and take our data, which is kind of old school but feels really good. And you do get to turn off, when you're taking a long exposure, some of our exposures are an hour long, you get to go out on the catwalk and just look up at the sky, and it's so dark that you can read by starlight. Like, it's really a beautiful place. You know, it is one of the darkest spots on Earth. But even so this is another telescope. This is the Keck Observatory. It's also twin telescopes. If you're going to build one telescope, to quote Contact, why not build two for twice the price? So this is the Keck Observatory on the summit of the big island of Mauna Kea in Hawaii. So this telescope is owned by Caltech, the University of California, and NASA. And so these telescopes are used by people all over the world. I've used this one, I think, 3 times. The competition for these telescopes is generally something like a factor of 5 to 1. So 5 times more people write in ideas for proposals than there's time on the telescope. And these telescopes allow us to see billions of light years, billions of years into the past. So this is, that's a professional photograph. That's my photograph. Up at the top, it's Global Selfie Day, so there we go. So, we share these telescopes, and in general, astronomers get maybe a couple days to a week to 2 weeks, if they're really lucky, a year on these telescopes. But even from Las Campanas, that dark, beautiful site where you can read by starlight, when your eyes adjust and you look at the sky, it's not black. It's dark, dark, dark blue. And that dark blue is because we live in an atmosphere, and that atmosphere is really a pain. If you're an astronomer, you wish that we didn't have an atmosphere. It would be so much better. But instead, so that atmosphere is glowing, and it makes it hard to see past. It blurs the light, like haze on your barbecue grill, and it's bright, and you're trying to see past it. So we put telescopes in space, both to get away from the brightness of our atmosphere and to study kinds of light that don't make it through our atmosphere, right? So some of our best telescopes, and this is what NASA's interest in astronomy is mostly putting telescopes up in space, or using telescopes on the Earth to support those telescopes that we've put in space. So this is Hubble after its last servicing mission. You can tell because it has the stubby little solar panels. And so Hubble is the most famous telescope in the world. It's also probably one of the most popular things the US government has ever done in terms of ask anyone in the world about Hubble and they think it's awesome, right? Hubble is a public telescope in every sense of the word. If you have an idea, you can write a proposal to use the Hubble Space Telescope. We get about 1,000 proposals a year. We just had the deadline, which is why I look a little tired. But there's about 1,000 proposals per year, and it's usually there's 8 times more proposals than there's time on the telescope. So 80% of proposals get rejected. It's cutthroat. It's really it's a bloodbath. But the reason and there's a committee of peers that sit down and judge the proposals and pick what we hope are the very best ones. And people from all over can use the telescope. Hubble was built by the United States and Europe, but it can be used by anyone. So if somebody from Australia has an amazing idea, they can get time on the telescope, which is really kind of neat and is not the way a lot of other governments run their science facilities, or even the way a lot of other science facilities in the United States are run. If you have a great idea, you can propose to use the Hubble Space Telescope, and it doesn't matter where you come from. And because these telescopes are so expensive, you don't get to be like Hubble and will your data to your successor when you die, right? Hubble the man. Hubble the man, I saw the box. There are boxes that he willed to Sandage, his successor, upon his death. For telescopes this expensive, we can't do that. And so all the data eventually go out to the public and can be used by other people, by anyone, not just the person who had that bright idea. And so if you want to explore, I have some websites here to explore afterward. The Hubble Legacy Archive is tons of fun. You can, in real color, look around and see some of the work that Hubble has done over the last 24 years. These aren't just the pretty publicity photos. This is all the data ever taken. And that's free for any researcher. So students who want to do science projects, it's all there. Yeah.
Can we ask a question?
Sure.
You've got a dark spot in the middle of that galaxy, and do you know what that dark spot?
Let's come back to that. I think that's an artifact, but let's come back to that.
Okay.
All right.
Don't forget.
Okay. You'll remind me. So Hubble is not the only space telescope. It's the most famous space telescope. It's kind of like, NASA has a family of space telescopes. Here are three that are close to my heart. Chandra, which works in the X-rays, which don't get past our atmosphere. Spitzer, which works in the infrared, which we can't see on Earth because the Earth's too hot. And Hubble, which works in the optical with light from the ultraviolet and optical. Okay? And those... this is the obligatory electromagnetic spectrum. The universe emits light in all colors, and to understand the universe, especially, we really need a family of telescopes that operate at different wavelengths. So Hubble sees in that little sliver of ultraviolet and visible light, but Chandra works out in the X-rays, Spitzer works in the infrared. We build these telescopes to work and capture all the light that we can from the universe. All right, so I don't have I could do a whole lecture on this, but let me just give you one quick example of why that's useful. So how many people know this picture? All right, this is the pillars of creation, right? This is one of the most famous pictures Hubble ever took. And so what this is a star-forming region where new stars are forming in a dusty cloud of gas that's collapsing. And off the top of the screen, that's out of the field of the detector, there are a couple big, bright, hot stars that are blowing out so much ultraviolet radiation that they're destroying the cloud. So when stars form, the biggest of them are burning so hot and blue that they actually rip apart the clouds where they were formed. So when you look at this picture, which looks so ethereal and calm, you have to think about, from the top, this rain of deadly radiation coming down from the top to the bottom, destroying these clouds. So stars had better finish forming and be done, or they ain't going to form because the clouds are going to be destroyed. And you see that in these funny little pillars, right? The clouds are being baked away from the top down. Now, the question is, have stars had time to form in those pillars before they get baked away or not? Well, you can't tell in the optical. This is an optical picture with the kinds of light that you can see. But if we look in the infrared, which is much better at seeing through dust than is the optical. So if we switch to the infrared here, we can see that the tips of each of those regions, I'm going to go back and do this again, but at the tips of each of these pillars, you can see a big, fat, newly formed star, right? So you can see that, yes, indeed, right? All right, look at the tops of the pillars. Okay. We can see that these new stars did have time to form. So that's one example of how having an infrared telescope complements what you can do in the optical. It lets you see through the dust, okay? And in fact, for this reason and several others, the new telescope that we're building to succeed Hubble is more infrared focused than is Hubble, because we want to see through dust like this. We also want to see back to the earliest parts of the universe, but that's getting a little bit ahead of my story. All right, so I'm going to spend most of my talk talking about what we don't know. So I thought I should give the last 100 years of astronomy a little credit and spend one slide on what we do know, because it's kind of mind-boggling. You know, we now know some of the big, profound questions that were the point of doing astronomy. You know, how old is the universe? We now know that number to several decimal places. When I was growing up, it was 10 or 20 billion years old. And it was that way from the time that shortly after Edwin Hubble discovered the universe was expanding until quite recently, when NASA's cosmic microwave background experiments gave that number to 4 significant digits. So we know how old the universe is. It's 13.7 billion years old. The Earth has been around for about 5 billion years of that history. We know that the Earth began at a Big Bang, that the universe began at a Big Bang. You may have seen the press releases about the BICEP 2 result and seeing echoes of that Big Bang and the polarization data. We now know, when I was a kid, there was this whole, is the universe going to have a big crunch and expand again and collapse, or will it expand forever? We now know there's not nearly enough mass in the universe to close it. It will expand forever. And in fact, it's accelerating. It's expanding out faster and faster and faster for reasons that we have no clue, which should scare the pants off of you. It scares me. Right? No, it's really kind of frightening, right? We know that what is the universe made of? The universe is mostly made of dark matter. Okay, what's dark matter? All we know about dark matter is that it has gravity, and it follows the laws of gravity, but it doesn't emit light. Doesn't absorb light, and it's not made of the stuff that's in the periodic table, which is what we're made of. So we have this bizarre universe in which the stuff that we're made of, the periodic table that we learned about in chemistry that has electrons and protons, right? That's 4.5% of all the stuff in the universe. And what the rest of it is a combination of dark matter, which is like a quarter, and then dark energy, which is like 3/4, and we don't know what either dark matter or dark energy are. Dark energy is the word that we're using to describe the fact that when we measure how fast the universe is expanding, it's expanding faster and faster and faster as we go from a couple billion years ago to today. We don't know what that is, and we don't know how fast. Is it going to rip apart the universe eventually? We don't know what's driving it. We don't know what the physics are. It's really yucky. But at the same time, that's really exciting, because it means that, for all that the physicists thought that we knew what all the particles were and that we understood electrons and nuclei, we got it all under wraps, there's more going on that we don't understand, this dark matter and dark energy. And so a lot of the focus of particle physics and of NASA's cosmology missions going forward are trying to understand, well, what is that dark energy? What is the dark matter? Okay. So we know a lot about our origins. The Big Bang turns out to be, shortly after the Big Bang, 100,000 years after the Big Bang, turns out to be observable from the microwave background radiation. That's great. One of the big questions is what happened in the next 13 billion years between after the Big Bang and today, and how do we evolve? How do galaxies like ours evolve? Our star is one of a couple 100 billion in our Milky Way. Our Milky Way is a fairly typical, a little brighter than average galaxy. How do you get galaxies like our own? Okay? Now, one of the coolest things about astronomy is that we can see that process in action, not in our own galaxy because we're too close, but by observing other people's galaxies. And this is such a cool idea that I'm going to spend a little time on it just to make sure you go home with this in your mind, because it sounds like magic, that we can use telescopes like time machines. It really just sounds like snake oil, just what? It's real. Telescopes act like time machines. We just can never see our own past, we can see other people's past. And the reason that that's true is that the speed of light is just really slow. I mean, it seems fast in daily life, although people are building straighter channels to Wall Street so that they can beat, they can find out, very fast trading a little bit faster than everyone else. That's dealing with the fact that the speed of light is slow, right? Most of the time, the speed of light just seems instantaneous to us, unless we send people to the moon, and then there's that weird 1.25 second delay when they're talking. Mission control says, how are you guys doing? And there's like 1.25. Oh, we're fine, right? That's just light travel time to the moon. The moon is 1.3 light seconds away. So when you see the moon, you're seeing 1 second into the past. Okay, that doesn't seem very exciting. When you see the sun is 8 light minutes away. So when you see the sun, you see it as it looks 8 minutes ago. Okay, really, that's not, what was I doing 8 minutes ago? Well, I was 12 minutes into this talk. Okay, not that exciting, but you are seeing into the past. And the reason that you're doing that is it takes light, the fastest thing there is, 8 minutes to travel from the sun to the Earth. When we look at Jupiter, that's 40 light minutes away, so we see it 40 minutes into the past, okay? Again, this is still part of our No, this is still fitting in the same day. When we look at the Pleiades, this is the Seven Sisters star cluster. You see it in the winter. It's also on the bumper of my car because I have a Subaru, which is which is named for that. That Subaru just means Pleiades in Japanese. So the Pleiades star cluster, which is a region of newly formed stars, is about 450 light years away. Okay, so that means that the light that when you go out and look at the Pleiades at night, you're seeing the light that left about the time Shakespeare was born. Okay, so a little bit of time traveling, but we were still speaking English. Okay, not that far in the past, but this is 450 light years away. Now the North American Nebula, this is a Spitzer image, is about 1,600 light years away. Okay, so the light we're seeing now from the North American Nebula left when the Roman Empire was falling. Okay, now we're getting a little, and this is all in our Milky Way, right? These stars are forming in our Milky Way, so are these. We're going to look at some other star-forming regions. This is Carina, a very big, very beautiful star-forming region seen by Hubble. It's about 10,000 light years away. It's okay, starting to get to Bronze Age. Let's just look through some of these. These are all star-forming regions in our Milky Way seen by the Hubble Space Telescope. And they're all really beautiful. We're all still looking at our own backyard, thousands of light years away. And this is where new stars are forming. Most of the stars that ever formed in the universe happened further long ago than that, billions of years in the past. And that's part of what I study, is I want to know how that happened. When did most of the stars that ever formed, how did that process happen? Okay, so this I have to bring up. This is, and lower resolution, sorry about that. Okay, this is an image that just came out from Spitzer that imaged the whole galaxy, our Milky Way galaxy, and it's a panoramic wraparound. And now we test whether the Wi-Fi is still working. It is. So this is something I would urge you to check out at home. This is called Glimpse 360. And it's basically a Google Maps of our galaxy. You can zoom in as much as you want. That's the center of our galaxy right there. There's a black hole in the center that's 2.5 million solar masses. And it takes a second lag. The light you see, this looks kind of washed out on the screen. That's because that's thousands of stars that aren't resolved, but you're just seeing as the total light you're seeing as a background. That's a star-forming region right there. You could spend hours zooming around. This thing just keeps going. Okay, got to catch up with the wireless lag here. This is Glimpse 360. This is public data taken by NASA's Spitzer Space Telescope. There's a star-forming region right there that you can just, should you be having a bad day at work, spend some time and wander through this. It'll make you feel better about our own galaxy. Okay. The other thing that's really cool I want to tell you about is that there's a citizen science project called the Milky Way Project that uses that data to help identify star-forming regions and bubbles. This is a bubble of blown-out gas where either a supernova exploded or something else exploded that blew it out. So this will walk you through how you can find these bubbles and you can identify star-forming regions. And this can be used by anyone around the world to do real science to mine this amazing database. So the two words, if you want to follow that up, are Glimpse 360 and MilkyWayProject.org. Okay? So that's an example where I didn't, the whole panorama of this, which goes all the way around, it was years of work by the Spitzer Space Telescope. It's a gob of data, because each picture is like a very tiny piece of that then gets stitched together into a mosaic. And that's the best view, it's one of the best views we have of our own galaxy. But so far we've just been talking about our own galaxy, and really that's our local neighborhood. Let's see if we can get a little further away. If you go out in the fall to a reasonably dark site, maybe not downtown DC, but go to a park or something, you can see the Andromeda galaxy, which is above the V of Andromeda there, which is our nearest big neighboring galaxy, and it's 2.5 million light years away. So now we're talking, we've got a million with an M. The light that is, and you can see Andromeda with your eyeball if you get to a dark enough site. I've seen it from the roof of the Penn State Astronomy building, and so it's easy to find in a crowded place if you know where to look. The light leaving Andromeda, 2.5 million light years away, left about the time that the genus Homo was emerging. So about the time the first human-like species were emerging on Earth, the light left Andromeda. Okay, now that's time travel, and you can do that with your eyeball or a pair of binoculars. You don't even need a telescope. You can see Andromeda. This is what Andromeda looks like with the Spitzer Space Telescope. You can peer through the blue, which is showing stars, the old stars that have already formed, and the red is showing where the new stars are forming. Okay, so it's another image from Spitzer showing how you can peer through the dust and see to the sites of where stars are forming. Now, let's get a little further away. Now we're talking a couple billion with a B light years away. This is one of the most crowded places in the universe. This is a galaxy cluster. The area you're seeing right now, in our own neck of the woods, there are two galaxies, Milky Way and Andromeda, and like a dozen follow-on dinky galaxies, okay? In this cluster, there are hundreds of big galaxies in that same space. So this is one of the most crowded regions of the universe. It's also one of the biggest gravitationally bound structures in the universe, okay? So this is a happening place. It's actually a very violent place. It's hot. Those galaxies collide with each other and make it hard to form new stars, which is why those galaxies all look very yellow. The other thing that is happening in this image has nothing to do with this galaxy cluster itself. It has to do with what's behind it. So take a minute and look. It's a little hard with the monitor, with the projection, but do you see any stretched out arcs around this image that look like your cat scratched the screen? Okay, you can see them at the top left of center. You can see at the bottom right. I'm going to zoom in on them right now. There are some of them. Okay, these are galaxies that, it turns out, these are galaxies that have nothing to do with this galaxy cluster. They're just behind it. And that galaxy cluster is magnifying the light from those background galaxies and acting like a natural telescope. Okay, so it's distorting those galaxies like a funhouse mirror, and it's making them brighter for our perspective. Okay, they look fainter to the rest of the universe as a result. And this is just simple optics. You can, let's see. So here's another example, a less crowded cluster and a more spectacular arc. There to the right, that's a background galaxy that appears 18 times brighter to us than it should be because this galaxy cluster is acting like a telescope. Okay, so this is fantastic. This is actually something that was discovered in the 60s and 70s, except that Einstein predicted it back in 1911, except he got the math wrong. That's where the oops is. Forgot a factor of 2. It happens to all of us. So Einstein predicted that mass should bend the path of light. That if you have light coming out of a laser pointer and you have a massive thing, the light gets bent as it goes around the laser pointer, or as it goes around the mass, right? Light travels in a curved space-time, and mass bends curved space-time. And so he predicted that if you looked at stars behind the sun during an eclipse, you would see that they weren't in the right place. They'd been bent out of position. Okay? And so the New York Times, with a great example of science reporting, reported it this way: lights all askew in the heavens, men of science more or less agog. Over results of eclipse observation, Einstein's theory triumphs, stars not where they seemed or were calculated to be, but nobody need worry. A book for 12 wise men. No more in all the world could comprehend it, said Einstein. Well, all of you comprehend it because I just said it, right? This light is getting bent by the mass, and the sun has mass. Okay, right? It's not that hard. But whenever I get depressed about current science reporting, just, it helps to go back to that from 1919. So this was the real confirmation of Einstein's theory, was that yes, mass bends light. Now, this charming fellow, Fritz Zwicky, who was as charming as that photo indicates, wrote an amazing paper back in 1937, which was this long, and I'm not nearly smart enough to write papers that short, in which he said that galaxies should bend light too. And in fact, it should work way better than stars. And so he predicted 3 things, all of which are true. I'm just going to, the first just says that it can test general relativity, Einstein's theory. Yes, it does. And the second says that it magnifies it acts like a telescope. It makes things look brighter so we can see further away, which is totally true. This is just a slide showing how that works, but it's, just light is getting bent. The path of light gets bent around a cluster of galaxies or any other concentration of mass. You're all bending mass, you're all bending light a little bit too, you just don't weigh enough. You're not dense enough, sorry. Okay, so why is that really useful? To my mind, our telescopes aren't nearly as powerful as I wish they were. And let me show you what I mean by that. So this is data from a recent paper taken with the Hubble Space Telescope. These are some of the sharpest images of galaxies that are we're seeing as they looked about 7 or 8 billion light years, 7 or 8 billion years ago, okay? So they're about half the age of the universe we're seeing back, okay? And you can see that, this isn't something wrong with my computer or the projector. They look kind of blurry, don't they? Right? They're not beautiful and sharp and clear like the close nearby galaxies that I showed earlier. And this is unfortunately just physics. As things get further away, they get smaller, and the Hubble Space Telescope is only so big, so it can only take pictures so sharp. There's nothing wrong with Hubble. It's actually the diffraction limit of light. It's a basic principle of optics. That to overcome this, to take a sharper picture, you have to build a bigger telescope. It has to be bigger. And Hubble, for all that we think about it as an amazing telescope, it's like the real estate thing. It's location, location, location. Hubble is only a 2.5 meter telescope. That's not that big anymore for a ground-based telescope. Ground-based telescopes are 10 meters across, the biggest ones. Hubble's 2.5 meters. Those are like the ones they let the grad students play with on Earth. Like they're not very big, just Hubble's in a great spot. So for Hubble to take sharper pictures than this, it would need to be bigger. We have to build a bigger telescope than Hubble that has a bigger mirror. Or we can cheat by using these natural telescopes and gravitational lensing, okay? So that's what I've been busy doing the last couple years, is cheating by looking at galaxies that have gone through one of these whose light has gone through one of these natural telescopes. Okay? Because you can see a lot from these images. I mean, you can convince yourself that the upper right one is a spiral galaxy and that therefore spiral galaxies like our own must have formed a long time ago. But, that's not the clearest image. It's a lot blurrier than we wish it could be. And again, that's nobody's fault. It's just physics. Galaxies are far away and faint. And so if we want to see how stars are forming in that galaxy, we need to take a sharper picture. Okay, so now for the cheating. So this is some science that I did with my colleagues a couple years ago. This is a lens galaxy, the big blue arc in the upper bit, part of the screen, that has been magnified by this cluster of galaxies by factors of, I think it's like that part is like 22 times brighter than it really is. So it appears magnified, both brighter and more stretched by a factor of 22 than it really is. And that, for my purposes, is fantastic because, and this is a picture taken with the Hubble Space Telescope. So I've used Hubble, which takes the sharpest images of any telescope we have, and then I've looked at an object that's behind a natural telescope. So I'm like bolting nature's telescopes onto our own best telescopes. That makes our telescopes, like Hubble, more powerful. Right? So, a bunch of us are doing this technique. Lens galaxies like this are quite rare, so we can only study hundreds of galaxies instead of thousands. But the universe has given these things to us, and they let us study things. They let us study galaxies in ways that we won't be able to do until we build much bigger telescopes. So this is from our paper, but the red regions just show places where the magnification is a factor of 100. So they're a little piece of this galaxy that have been magnified by lensing by a factor of 100. And so what we did is reconstruct what that galaxy looked like before it got all weird and distorted in the funhouse mirror of lensing. And you get this reconstruction. This thing is this is a merger of two galaxies that are slamming into each other. And then stars are lighting up and forming throughout the arms. At the left is this tail of debris that's been ripped out of the galaxy on the left because of this collision. And this is much sharper than, if we go back a couple of slides, than we can do for regular galaxies that aren't sitting behind a gravitational lens, right? So that's the trick. And you can do all sorts of fun with that. You can spread the light out into a spectrum, and you can study the composition of this galaxy. Suffice to say, in a lot of ways that seem illegal. Because if the galaxy wasn't 20 times brighter than it really is, like, you just can't do that. You'd have to spend weeks or months or years at the telescope instead of an hour or two. All right? So the work that I've been doing with my colleagues at the University of Chicago and University of Michigan has been getting hundreds of these galaxies. So my colleagues have found hundreds of cases where there are these gravitational lenses. And you can see these big blue arcs, which is how they find these, that pick out these clusters of galaxies as being good lenses. So what we've been doing is pointing the Hubble and Spitzer space telescopes at these rare gravitationally lensed galaxies to study that star formation in much better detail than we normally can. So that's like 10 minutes of ground-based data in kind of bad weather, so they look all kind of blurry. And now I'll show you the sharp pictures that we've taken with the Hubble Space Telescope. So just as a personal story, you know how I said that Hubble is really oversubscribed, like that many more people want to use it? We had to write this proposal we put in this proposal for 3 years before it got accepted. So we finally got this thing accepted to go look at these clusters, and this is the kind of data that we got. So this is all brand new data taken within the last year that we're actively working on. But you can see the clusters of galaxies. The yellow things are the galaxies in the cluster that are acting like the lens. And then the blue and red things that look arcy and stretched are these galaxies that have been magnified and appear much brighter. Let's hold that. Is it fast?
I don't know.
Go for it.
How do you map the squiggles so accurately? What do you use to base your calculation of the...
Why don't you ask that question again in the question period? Because I definitely want to get to it, but I don't want to interrupt the flow here. So one of the things we have to do is accurately map the squiggles here, is reconstruct the lens. There's a lens here. It's basic optics, and map where the cluster galaxies are, and use that to reconstruct how these galaxies look distorted to us. That process actually works. It's still surprising to me, but it really does work. So we can reconstruct these images. So these are just some of the clusters that we've obtained. The big blue thing in the middle center there, bottom center, is again like 20 or 30 times brighter than it really should be. And so there are these fantastic examples where these are typical boring galaxies that normally Hubble could barely see, or it would be a little smudgy thing to Hubble, that are instead getting stretched out and magnified so that we can study them. And there are often multiple galaxies behind a given cluster, so each one of those numbers just says how far away it is. Higher numbers are further away. And so you get multiple galaxies behind the cluster that have been magnified so that we can study them. And so that's what I do now. When I go to these observatories, I use spectrographs to study these galaxies. And what I want to know is mostly what do they look like inside, and how quickly are they building up their heavy elements? How quickly are they building up their periodic tables, right? Because all the heavy elements formed in stars, and we can chart how fast that process happens, that we build up heavy elements like iron and carbon. So just more of these. We've got 37 of these clusters. So the work that we've been doing is trying to build a much bigger sample of bright lensed galaxies that we can study, because it's what we can do right now before we have bigger telescopes to study that evolution of galaxies over cosmic time. This one is almost an Einstein ring. It's just a really gorgeous example of lensing in action. I could do this all day. But I want to finish by saying why we still need to build bigger telescopes. So in cases like this, the universe has been very, very kind to us. And it's put a big natural telescope out in space and then stuck things behind it that we can study. But you can't point it. You can't observe, the certain kind of galaxies that you'd like to study. And you're limited to samples of only a couple dozen to a couple hundred galaxies. For many problems, you would like to get beyond what we have in terms of current telescopes with Spitzer and Hubble. You need a bigger telescope to both make things sharper and clearer and to just get more light and see things that are fainter and further away. So, as Jennifer mentioned in the introduction, I'm a project scientist on the James Webb Space Telescope, which is NASA's highest priority science mission. It's launching in 2018. And that's a telescope that is designed to come after Hubble and to do the things that Hubble can't do. It looks very different than Hubble. It doesn't have a tube. It's cold. It's chilled down to 40 degrees above absolute zero. So that it can work in the infrared, and it's far, far away from the Earth. It's orbiting. It will go out past the distance to the Moon to get it away from the Earth because the Earth is hot. So I want to show you some pictures of recent progress on that. This is the science instrument. That strange black jungle gym that there are people climbing inside of is where we're putting our science instruments. There are 4 science instruments that get bolted together. This is the silvery thing on the left is the 4th and final science instrument getting bolted on. There was a moment of, it is a little frightening when you see the thing that the science instruments hanging from the crane being lowered into the jungle gym. But all 4 of our science instruments have been built and are in-house, and those are what will allow us to study distant galaxies and to study that process of galaxy evolution a lot better than we can with Hubble, just because it's going to be about 100 times more capable than Hubble. Here are some of the mirrors. Hubble has a big fat glass mirror. The mirrors for the Webb telescope are this lightweight beryllium with gold on top. Each one is about me across, minus my fingertips. For scale, that guy helps show that. All 18 mirrors are done. There they are in their protective case. We don't let them out much. So the mirrors are done, the science instruments are done and being tested, and then this whole thing has to hide behind a sunshade that is the size of a tennis court. That, just to remind what this looks like, that sunshade is the size of a tennis court, and it hides our telescope mirrors and the instruments from the sun. And so on the bottom side, it's room temperature. It's, it's at the distant, it's, 80, 70 degrees. And on the cold side, it's 40 degrees above absolute zero. So what is that? Minus, I can't think in Fahrenheit, but at low temperatures. But, it's several hundred degrees centigrade below zero. And so it's really, really cold, 40 Kelvin, so that the telescope can work in the infrared. And so the reason that, this, for scale, this is 6.5 meters across, Hubble is 2.5. We've designed this telescope to do a lot of the things that Hubble just can't do because it can't work in the infrared and it's just not a big enough telescope. So with that, I'm going to stop and take questions, and we can talk about lensing geometry and things, but I want to give everyone a chance to ask questions. Thanks.
Do you want to do the thing in the middle and then the calculations and then other questions?
Sure. I don't know what the thing in the middle is, but I can get back to you.
There was the picture, and you said there was something in the middle.
Yeah, I can go back and look that up, but I don't know that off the top of my head.
And then the calculations.
Yeah, the lensing reconstruction. Yeah.
Somewhere.
So the question was, how can you determine with such accuracy the path of those squiggles and how it's meant? Is it based on the mass of the existing visible galaxies, or is it based on many other things?
It's actually, it seems really improbable that this should work. But so my colleague Karen Sharon at the University of Michigan is the expert on this. She's a magician. What we do is she takes where the cluster galaxies are, so that tells you more or less where the mass is, at least a first guess. That's where the galaxies are. Then there's a whole big bunch of dark matter on top of this that she assumes has a pretty simple profile. It's elliptical, and you can twist it around, but it's not allowed to be arbitrarily complicated. And then she uses the positions of where all the background arcs are and their redshifts, how far away they are, which we've measured from our ground-based telescopes. And it turns out that's enough to solve the problem. So what she's doing is she's mapping where the mass is in the cluster. And then that is acting, it's called ray tracing, because it acts like a lens. In the same way that you can ray trace glasses or the mirrors and lenses in our instruments, you can treat this just like a lens and map how the light passed through it. It helps when you have Hubble data like this, because the same galaxy, I'm going to have to go back a few slides here. Okay, I'm going to cheat. There we go. The same galaxy is actually imaged multiple times. If you look at this, there's actually there's interesting symmetry, but the galaxy appears 5 times. There are multiple images of it. And so that helps constrain the problem, because the red bit that you see in the arc appears 1, 2, 3 times there. So that helps nail things down. It still kind of amazes me that this works, but it is actually a very robust process.
It appears 3 times this way or this way?
Oh, you're going to make me use my laser pointer. You're going to make, okay, sorry, I was not using the laser pointer to make the WebEx people happy, the web presentation happy, but see this red bit? That's the same red bit here. It's the same red bit here. This whole thing is one star forming region. It appears again, oh gosh, where is it? This thing is that thing. Right, so there's a symmetry. The monitor is not quite doing it justice, but there's a symmetry that lensing gives you, where the images appear multiple times. Yeah. Other questions?
Are the telescopes, the space telescopes, are they only viewing, or are they also listening as well?
Are they only viewing, or are they listening as well? It depends. So are they doing other things other than electromagnetic radiation? NASA telescopes in general, just thinking about different NASA telescopes cover the X-rays, the gamma rays, the optical, the UV, the infrared. There have been some experiments with radio telescopes, so doing light, but light in the radio wavelengths as well in orbit. That's been kind of a specialized experiment, and it's a pretty a small field.
Is that going to be expanded with James Webb?
So James Webb studies light from, it goes as blue as, someone have a nice red shirt, that nice maroon cardigan, sorry, just to pull you out. That's about the bluest color of light that the James Webb Space Telescope will be able to see, is a nice maroon. So it starts at maroon, and then it goes to redder than the eye can see, to 27 microns, which is about where things that are the temperature of humans peak. So we're all emitting light, and I didn't bring my infrared camera, but if I brought my infrared camera, you would see, and we turn all the lights out, you're all glowing, and you're all glowing at a wavelength of light in the infrared that the Webb telescope can see. Because we want to see planets around other stars that are about as hot as humans are. So we build a telescope that is optimized for those infrared wavelengths.
Yes. Will the Webb telescope be able to observe planets around other stars?
So the question is, will the Webb telescope be able to observe planets around other stars? And yes, that is one of our key science goals. So I study galaxies far away, so that's kind of my bias at the talk. But the Webb telescope will do that really well. That's one of its key goals, is to find that first generation of galaxies that formed after the Big Bang. But we're also building it to be very good at seeing planets in a variety of ways. One of the key ways, there are coronagraphs, which is a very high-tech way of sticking your thumb in front of the star and then being able to see the planet because you've blocked out the star. But there are coronagraphs on board to do that. There are also spectrographs that can look at the spectra, the rainbow of colors coming from the star plus the planet. And you take that when the star's in front and when the planet's in front of the star and the planet's behind the star, and you subtract the two. And that gives you what the planet is putting off. Star plus planet minus star gives you planet. That can give you the atmosphere of the planet. Now, one of the long sought things that people want is to get signatures of the atmosphere, like water, like carbon dioxide, like methane, from planets. Webb can certainly do that for big planets like Jupiter, planets like Neptune. One of the things under current debate is whether or not we can get an Earth or a super Earth, something that's more massive than the Earth, but a rocky planet. It really kind of depends how kind the universe has been and how close the nearest Earth-like planet is. But one of the key goals for NASA astrophysics is to locate the nearest planets, the nearest stars that have planets, Earth-like planets, and then point telescopes like Webb at it and try to get the atmospheres and see whether it has conditions like water that would support life. Now that's a big goal that spans many missions. You may have heard of the Kepler telescope. So Kepler stares at Cygnus the Swan just nonstop, and it's found thousands of planets that move in front of their parent star and wink out and cause the star to get like 1% dimmer and then bright again. Those planets are very far away, so they're really hard to study with a big telescope like Webb. So one of the things people are working on now is trying to study the nearest stars around our sun, because now we know the results from Kepler. We know how many stars we would have to look at to find Earth-like planets, because we know how common they are. They're really common. That's what we know from Kepler. Your average sun-like star has a planet, has a small planet. That's really cool. So there's now effort underway. There's a new instrument called TESS that's a small mission that's supposed to launch in the next couple years to go survey the nearest stars and see whether they have Earth-like planets. And then Webb could look at them and look for things like carbon dioxide and water. Sure, all the way back.
If you have a dip of, say, 1% for an Earth-sized planet that goes in front of a star, how do you tell the difference between that 1% dip and something that's 10 times bigger than the Earth but only does a glancing blow, so only 10% of it hits? How can you tell the difference?
So the question is about figuring out different kinds of transits when planets move in front of the star and what that tells you. And let me back up and say that I think 1% is for a bigger planet than the Earth, and the Earth-sized planets make much smaller dips. So I messed that up. Wanted to fix that. So the question is, so yes, the Kepler. If you've been paying attention to the media, you've seen that Kepler announces candidates, but not planets. And then like a year later, they'll come back and say they have planets, and then some more candidates. It's very cautious. And the reason for that is that there are multiple ways that a star getting a little bit dimmer and then brighter again could be misinterpreted. So the simplest way is that there are star spots, right? Our sun has star spots. And so that's an easy way. Those shouldn't repeat. So that's why Kepler has required it to come back on a regular schedule so you can get an orbit. There are also things like it may not be hitting, yes, it could be a glancing blow. And so what people model, I don't do this, but the people who do this, they model how it goes in, how the light gets fainter, how quickly the light gets fainter and then gets brighter again. And the shape of that, you can draw yourself circles with construction paper and convince yourself that what fraction of the star is obscured is, it'll change the shape of how quickly it gets fainter. Does it just foomp, or does it kind of slide off, right? And these guys are wizards, and it's all very cool that this works. But those are the techniques people play.
There's time for one more. Yeah.
Okay. Why don't we do the kid in the front?
Yeah.
Yeah.
How do you keep telescopes safe from space junk?
Oh, that's a great question. The question is, how do we keep telescopes safe from all the stuff out there that wants to kill them? So that's from space junk. That's a really good question. So Hubble gets hit kind of a lot by little bits of junk. Much of it made by humans, right? Pieces of rockets, paint, stuff that's up there from all the years we've been launching stuff into space. When the astronauts repaired Hubble on each mission, on several of the missions, they put in new protective layers because they saw that some of the mylar was like hanging off because it had been hit by little micrometeorites, both natural, little asteroids, as well as paint, pieces of rocket, stuff like that. That's just a problem, and we worry about it. Hubble does get put into a safer position when a big meteor shower is happening. So we know there's a big meteor shower. They're on schedules, right? But we will turn Hubble so it's kind of presenting the smallest profile right, to the storm, which doesn't help a lot, but at least, it's kind of like playing dodgeball. You try to get small. So we do that for big meteor showers. Also, the Air Force keeps track of the bigger pieces of space junk. And I know there have been times when they've told the astronaut, when they work when the astronauts have worked on Hubble around when they thought there were big pieces of junk. So not like Gravity, the movie. So some of that we can do. Some of that we just build our telescope to be able to take the small stuff. So you look at our beautiful sun shield here. So this is the James Webb Space Telescope. There's this sun shield that keeps the, so this picture is wrong, by the way. The mirror should be dark. If there's sunlight on the mirror, we're doing something wrong, because the sun, the whole point of the sun shield is to hide the mirror. So the sun is supposed to be at the bottom of this picture, and that sun shield is hiding the telescope. The telescope's cowering this in the shade. That sun shield is 5 layers of a really thin material that looks like what potato chip. It looks like the plastic bag that potato chips come in. It feels like it too. It's kind of hard to rip. It's strong. There are 5 layers of that sun shield that get tensioned up on springs. We don't actually need 5 layers. It's there so that if it gets hit and it gets ripped, then we have extra layers. And the material, it looks like kite fabric in that it has it has stuff to rip stop. Like kites have that cross-hatched pattern to keep it from tearing, so it'll just tear in a small piece, but it can't spread. We have that on our sun shield too. Because we expect that it's going to get beaten up. So this telescope is going to go out past the orbit of the moon, so it's not going to get hit by Earth, by stuff we've launched, but it's going to get hit by little pieces of meteors, by asteroids and stuff. And so we just have to, it turns out there are measurements of how much of that stuff is out there. And so our engineers tell us how likely every piece is to get damaged. And then it's built with some layers of protection. In the case of the sun shield, there's just more layers than you need, so it can get ripped up. For some of the other bits, there's like actual shielding around some of our sensitive electronics. That said, there are big things out there, and sometimes you get really unlucky and you get clobbered by a big thing. I know the Suzaku telescope had a micrometeorite go through one of the cameras. And they were like, the camera stopped working, and it sent like alarms, and and they're like, what happened? And the nearest they can figure out, it got slammed by a meteorite. Now they had other cameras, so they just stopped using that one. But sometimes that stuff happens and you're just like, that's not good. So some of it is hoping, but a lot of it is engineering and trying to build it strong enough that it's strong enough to take what you expect happens. And if you get really unlucky, you get really unlucky. That's a good question.
Thank you.
This has been a presentation of the Library of Congress. Visit us at loc.gov.